Okay, so now we're going to learn all about thermochemistry. Thermochemistry. Look at that. Wow, it's the Hindenburg. Let's talk history. Oh, look, explosions. Ooh, ah. And what's this thing? Well, we'll talk about that in a little bit. Okay, so what does thermochemistry mean? Thermo means heat, and chemistry means chemistry. So it involves chemical reactions that involve heat. And here's some words that you guys should remember. We have exothermic, which is energy coming out. A reaction releases heat, it makes things hotter. So reactants, products, notice the reactants are going in and the products are coming out. Notice heat energy is coming out. And look, it's a barbecue. Oh, the weather's going to be nice. Let's barbecue. Okay, so that is exothermic. And then, of course, there's endothermic, where it absorbs heat. So it feels colder. Notice where the heat is. It's on the inside. So its heat goes in. So heat goes into the ice cube. So if something feels hot, it's exothermic. And if something feels cold, it's endothermic. What is energy? Well, energy is the ability to do work. What kind of work? Oh, well, homework maybe? I don't know. Do you have energy to do your homework? I hope so. Okay, so how do we measure energy in the sciencey world? Well, there's two ways to do it, or there are many ways to do it. We use something called the joule in the science world, which is a measurement of energy. But of course, you might be a little more familiar with the word calorie, which is a dietary unit of energy. So look, source of energy, look, source of energy, look, nuclear source of energy, and look, Big Mac source of energy. Nice, I know. Okay, so what the heck is a calorie? Well, we look at our labels of food. Now that we're stuck in the house, maybe we're reading our labels. Calories tells you how much energy you get from that food. So the more calories it has, the more energy you have. So if you eat too many calories, not so good. We'll talk about that later. So what the heck is a calorie? Well, a calorie is the amount of energy needed to raise the temperature of 1 milliliter of water, which is a tiny, tiny amount, 1 degree centigrade, which is tiny, tiny amount. So a calorie is a small amount of energy. But Mr. G, it says calories. It's only 60 calories. It's like nothing. Well, the calories with the big C really is not a calorie. It's actually a kilocalorie, which is 1,000 calories. So really, it's not really 60 calories. It's really 60,000 calories. So when you're eating that, just think about that for a second. How do you measure calories? Well, in a lab, you would use this thing called a bomb calorimeter. You put your stuff inside there. It's got oxygen. You heat it up, and zzz, and you light it on fire. It burns inside. You have a little stir. You have a little thermometer. You know how much water's in there, so you can figure out how much energy that was in the food when you burnt it. Well, that makes sense. Now, of course, we don't have such a fancy schmancy piece of equipment in the lab, but this is what we would have done, and maybe I'll share a picture with you from our other labs where we take food like cheese doodles, yum, and we burn them underneath some water, and we'll see what the results were to see how close the label of the food and our data is the same. Okay, so once again, food is measured by calories. So let's talk about how many calories in a gram. Well, let's see. Ooh, if you're into carbs, it's 4 calories per gram. If you're into protein, that's 4 calories per gram. But look at the fat. Oh my goodness, it's 9 calories per gram. So for every gram, you get 9 calories from the fat and almost half for the carbs and protein. So, too much fat, not so good for you, too many calories. So, how do we get our energy? From food? Well, look, it's a sciencey thing. We get our energy from food by breaking and rearranging the bonds in the food, which releases the energy. So here's an example, not that we really eat hydrogen, but if we burned hydrogen, we have hydrogen bonds, here they are, and then we have the oxygen bonds. Oh no, Lewis dots? Okay, just bonds, okay? So we got bonds here and bonds here. And what we do is we break the HH bond and we break the OO bond and then we make OH bonds here and two OH bonds here. So we're rearranging these bonds. And by doing that, this one gives off energy. Now, of course, this is what we do. We take sugar, which is glucose, and we add oxygen. That's what we breathe. And hopefully you did some mindful breathing on Monday. So we have get oxygen in our bodies, and the oxygen is in our body converts that to carbon dioxide, which we breathe out, water, which we also breathe and sweat out, and also pee out too. And of course, if you remember your biology, if they bothered giving you this number, you get 38 ATPs. ATPs is the energy that our body uses. So we don't burn sugar, but we do burn sugar by doing chemical reactions, which make these little ATPs, rather than a barbecue, which we really don't want to spontaneously combust. So it's not fun. Okay, so once again, here's the review of the biology from last year. You eat your chemical energy, carbs, fats, and protein, yum, yum, yum. Your body converts it into ATP, and then your body uses the ATP to do what it needs to do, like pay attention, exercise, so on and so forth. And what comes out? Food in, guess what comes out? CO2 comes out because you're breathing out the carbon dioxide. Water comes out. Heat comes out. You have 98.6 degree temperature, which you should, and if your temperature is any higher, it means you have a fever, and you gotta watch out if you not feeling good and you got a fever. There's a nasty bug going around that you might have heard about, so that your body raises its temperature to get rid of the bug. So how does it do that? It burns these calories to make heat. Okay, now here is the balanced equation. We have some glucose, we add some oxygen, we get some CO2, make some H2O, and make some ATP as energy. So now, of course, maybe you're at home, and what do? Well, you take some glucose, or this is sugar, regular sugar. This is sucrose, sugar cubes. We take a little bit of oil. We take a little bit of vanilla beans. We take a little bit of flour. We take a little bit of eggs. We take a little bit of chocolate. And we do a chemical reaction and mix them together, throw them in the oven, and lo and behold, ding, 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 chocolate cake. Yum. Okay, so, Mr. G, I want to talk about this counting calorie business. What's the scoop about counting calories? Well, it's all about thermochemistry. Oh, but what about this low calorie, low carb diet, high carb diet, low protein diet, high protein? Yeah. It's thermochemistry. Energy in versus energy out. If you have extra energy in, your body converts that extra energy into fat. So it's a question of balance, and we're going to talk about equilibrium later, but look, it's balance. So here's your balance. So here you have an exercising person. Hopefully you guys are getting some exercise, and food. So if you're sitting at home watching Netflix and eating and just hanging out and being a couch potato, you will turn into a potato because you will end up gaining weight. If you ate as much as you burned, your weight would remain the same. If you want to go on a diet, you exercise more, eat less, and you shift that equilibrium here towards weight loss. So if you gain weight, you're eating too much food, and if you exercise more, you lose weight. Now, of course, this is an amusing question, which I love to pose to the class, is, let's see, which one's better for you? Cheeseburger or apple? Well, the apple weighs more. So does the apple have more calories? Oh, I don't think so, because guess what? The apple is mostly water and a little bit of sugar and a little bit of protein, so a little bit of carbs, so tiny bit of carbs, and look at all that delicious fat. Okay, so let's compare. You got a 100-calorie apple and a 100-calorie soda. Are they the same? Well, from a thermochemistry perspective, surprise, they are. But, from a healthy perspective, I would guess the apple is more healthy for you than the soda. But of course, you guys know what I would choose to have in the middle of the day, and it would not be the apple. So,
Pepsi.
Yeah, Pepsi, Coke. So, let's talk about the conservation of energy. What's the conservation of energy? Energy cannot be created or destroyed. So, what does that mean? You kind of guys knew that already. So, there's different kinds of energy. So, here's two kinds of energy, which are fun. We have kinetic energy and potential energy. Kinetic energy is, hopefully you guys did your vocab list, the energy of motion. Potential energy is stored energy. It is your potential, just like Pinocchio would say, "Oh, I see all these people with potential." Ooh. So, that's potential energy. So, energy can be changed from one from the other, but it cannot be created or destroyed. Okay, so for example, and this for those folks who are taking physics next year, you'll get into this, and I'll show you a really cool What the What Wednesday on Wednesday about converting kinetic energy and potential energy, which is super duper cool, which you should try at home, but be careful about doing it in the house. We have energy going in. So you're riding your bicycle up a hill. I love this analogy because you'll see it in a little bit. You have energy going in. You're riding the bicycle up. And you get to the top of the hill, you're all exhausted. Well, guess what? You put energy in. The energy from what? The energy of you riding your bicycle. Okay, so that's energy that you put in. You put kinetic energy in by riding the bicycle up the hill. Now, of course, where did you get that energy from? Well, from the cheeseburger that you ate earlier. That's where it's food energy. So you got food energy turned into chemical energy, turned into potential energy. Wait a minute. We're talking about chemical energy, potential energy. Didn't we have chemical energy and electrical energy last unit? Oh, yeah, we did. Hope you answered that right. Okay, so then we have potential energy. You're at the top of the hill. You have the most potential, but you're not moving because you're just sitting at the hill. You're taking a break because you're so tired from biking all the way up that hill. So now you're just hanging out there. You got lots of potential energy. How do you know? Well, guess what? You start going down the hill. Do you pedal your bike on the way down? Hell no. You go all the way down, and it's the gravity that pulls you down, so it's gravitational energy being turned potential energy into kinetic energy. And as soon as you get to the bottom of the hill, what? That is a lot of potential. You've got a lot of potential. Okay? That's a bad Pinocchio voice. I'm sorry. Okay. So, we have energy. Can you do better? No. Okay. So, we have energy going in, energy going out, going from kinetic energy to potential energy, back out. But during this whole process, energy is just converted from one form to another. It is not destroyed, not created. So, it's food energy, converted to muscle energy, converted to potential kinetic energy, converted to potential energy, and then back out again. Oy. Okay, so what kind of energy is there? Well, let's see. There's a bunch of other kinds of energy. So let's see. There we go. Here they are. Here they are. Oh, I'll go back. So we got energy. Energy is the ability to do work. So you have chemical energy. Chemical energy is stored in chemical bonds. So chemical energy could be in bonds. It could be stored chemical energy in a battery, which we just covered earlier. Nuclear energy is the energy that's stored in the nucleus of the atom. Then we have, and that's the energy from the sun. Then we have electrical energy, and that has to do with electricity. So we got our little battery. So that's chemical energy converting into electrical energy. And then there's something called thermal energy, which we're going to be spending a lot of time on. And the thermal energy is the kinetic energy of particle motion. What does that mean? Particles are moving, and it's heat. Okay, so here's chemical energy being released, kaboom. Here's solar energy being converted into electrical energy. That's what solar panels do. Solar energy to electrical energy. Here we have chemical energy converted to electrical energy. And here we have, hot, warm, and cold. That must be thermal energy. So let's talk about thermal energy just for a second, and then that'll be all. Okay, so thermal energy, what the heck is heat? Heat's thermal energy that flows from something that is hotter to something that is colder. And that is something that my little guy just learned 2 weeks ago in his science class, right? You do. So, hey, this is 6th grade stuff. Heat goes from the hot to the cold. What is heat? It's the speed of the particles. So the faster the particles are going, the more kinetic energy it has. The more kinetic energy it has, the more temperature or thermal energy it has. So kinetic energy and thermal energy are kind of related. How can they be related? Well, you take your hands, you rub them together really fast. That freaks you out. I'm rubbing my hands together really fast. My hands are getting warm. What am I doing? I'm converting that movement of energy. I'm moving the molecules in my hand faster and faster and faster. And that friction, which you'll learn in physics, that friction moves the molecules faster, which faster moving molecules is heat. And the slower moving molecules are slow or cold. So you can't really, Mr. G, it's going to be really hot soon. If I turn on the air conditioner, I'm going to cool things down. No, you're not. You're not going to cool things down. You're actually taking the heat out of your house. And if you went outside and you felt the back end of your air conditioner, you'd notice it's really hot out there. Why? Because it's moving heat from the inside of your house to the outside of your house. And now I hear my refrigerator making a noise. Guess what that's doing? It's doing the same thing. It's converting or taking the heat that's inside the refrigerator and taking it outside the refrigerator, which is why either the space on top or the space behind or the space underneath your refrigerator feels a lot warmer. Ever notice why? Now you know. All it's doing is it's transferring the heat out of the refrigerator. That's what it's doing. It's not cooling things down. It's unheating things down. I know that's strange, but it's the way it is. Okay, so let's double check. See if you guys paid attention, because I didn't turn this into a quiz ed puzzle, so the ed puzzle comes later. So, when you touch ice, heat is transferred from your hand to the ice or ice to your hand. Which way? Which one's warmer? Your hand. So the answer is your hand to the ice. So Heat is going from the hot thing to the cold thing. When you drink a hot cup of coffee, heat is transferred from your mouth to the coffee or coffee to your mouth. Which one's hotter? Hopefully it's the coffee. So if it's, it says hot cup of coffee. So if it's a hot cup of coffee, the answer is it's going from the coffee to your mouth. But Mr. G, what if I'm drinking iced coffee? Aha! That's the other way around. So actually, you're heating up the iced coffee, which makes you burn calories. Is there an iced coffee diet? I don't know. Okay. So, we'll save the cat for tomorrow. Okay, so we'll save this for Friday for the rest of the video. And yes, there is a cat coming. You saw a sneak peek. So, do your vocab, and here you go.